Speaking of reliability, a podcast with good friends talking with you about reliability engineering topics. Welcome to Speaking of Reliability. This is Fred Schenkelberg.
And this is Kirk Gray.
Hey, Kirk, I understand you got an email the other day with a couple of interesting questions.
Yeah, I have somebody who contacted me and is about to start she's terming, and she took a webinar on HALT, an engineer, and started talking to me about doing a multiple environmental overstress test, MEOST, which I heard of it long after I worked with Gregg Hobbs and HALT and HAS, and just read a presentation by ASQ on it. That's posted on the web, a slideshow. I think it's 2013, somewhere way back. But it's very, very, very similar. In fact, I didn't see a lot of differences between that and HALT in the way this individual at ASQ was describing it, and that is first find out the individual envelope.
Given the old days of Gregg and the I'm drawing a blank on who the other McLean? No. Who's the other author?
Harry McLean?
Harry and Gregg, they were suing each other who had this term and did that. And so I can understand other authors just saying, I'm skipping HALT altogether. I'll write my own book.
Well, right. And we go to, you talked about HP and Strife.
Yeah.
Everybody's had some kind of stress test. Some have used just burn-in, which we all know.
In times it was because you had a known,
depending on the mechanism, you get lucky and it was a chemical mechanism, you'd probably have some acceleration.
Yeah. But anyway, there's lots of different terms for it. So anyway,
right.
MEOST, I've seen in
everybody has to have their own invented here thing.
But what do you but you understand from this question is that this is an application of what is similar to what we would call HALT or HAS. Is they're setting
HALT.
Is it just HALT?
HALT.
They're not doing a screen?
I think they run the two together. HALT and what I consider two different processes. The HALT is to find limits and find possible weaknesses and compare limits. And then the screen is using every stress you can combined to accelerate fatigue damage, to determine.
Well, I didn't get it from the question. Are they setting up a screen or are they just doing a test to discover faults? Because part of the question was could you predict what the faults will be? And I was like, well, that's a silly question.
Yeah,
isn't that the point of doing the test? Is to figure out what they are?
Exactly. Can you point out what failures will occur in digital systems when you run MEOST? And I'm thinking, well, first of all, if I had to go look up what MEOST, but it's just another acronym that somebody came up with because, Gregg
were taken.
Well, and Gregg was sensitive about anybody using HALT and HAS, and he wanted to take a royalty for anybody using that term, but he never did, and it became a general term. And as we've talked about before, people call something HALT, and it's not when you talk to them what they're doing.
Oh, right. So what was her question though? She's trying to set this thing up
over in a overseas lab. Okay. Mm-hmm. And I've worked and been to many labs in Asia.
Oh, I get remote labs even across country, and it's hard enough.
And I've also been part of a company that directed those companies overseas to do a HALT test. And I would get back the reports saying this diode or this resistor fell off at, 5 G's RMS.
Exactly as expected.
Exactly as expected. And, I'm going, no, you didn't expect it. You never knew. There's no specification for G RMS on the holding of a resistor or a device. In fact, I don't think any component has a vibration spec.
Well, some do. Yeah, like microphones and stuff like that.
Well, yeah.
But things with open parts. Yeah, exactly. MEM devices often do. But one of the issues that I run into is that there's a logic to those reports. It failed because it failed. And so that's when we should expect it to fail. And it's sort of that kind of logic. If it failed, that's when it's expected to fail.
Exactly. It was always overspec. It's always overspec, of course.
Right.
I mean, but that's the big challenge.
You get that walking across the room.
Right. It's really difficult to get the orientation of working from the perspective of the strength of materials and what strength of products can be or can be. Not, they certainly have to meet the environmental use conditions. But the thing is not really thought about is the repeated worst case environmental stress conditions being.
Well, it's not even repeated worst case. It can be pretty benign. And I found in HALT that, vibration's my favorite one, is that if there's two set of materials on your product that can move relative to each other.
Yeah.
Unless that's accounted for in the design, it's usually a bad thing. You're going to get metal filings where you don't want them. You're going to get wearing of insulation where you don't want it. You're going to get shorting where you don't want it. You're going to get parts fatigue cracking and falling off. Anything that can move that. And it's a completely different mechanism than just temperature, right? With diffusion and chemical processes.
Right.
But it's one of the things I found in HALT, especially the vibration part, is that vast majority of people think, well, I put the part on the board, it's soldered, it's not going anywhere. And it's a 4-pound device sitting 2 inches up on 2 little spindly leads. You should be able to predict that is just not going to work. This thing's going to be a great big mass floating all over the place.
Right. And that's why HALT vibration was so effective on power supplies because they're so 3-dimensional. Whereas you get a flat circuit board or, you try and just think of an iPhone internal circuit board,
it's packed like a brick, and
it's like a solid.
They couldn't put conformal coating in there because there's any room.
There's no room. But
they couldn't pot it if they tried to.
I would be curious is how long you could run a HALT repetitive shock table against those. I think it would be quite a long time.
Oh, I don't know. Just give it to a teenage, one of our unionized teenage daughter.
We know it breaks. We know that the glass breaks. Okay.
Yeah.
And water is a problem. Has been a problem, but water is not so much.
Not so much anymore. Yeah. No, they're getting better. But anyway, so she's trying to do this remotely, and I think there's just cultural approaches to dealing with failures. Some people explain away, well, it failed. Well, of course it failed.
Right. As opposed to we've tested a lot of other products of this type, and they're all capable of going to 70C or 80C or 150C.
Well, then you get that was, 1 in 1,000 that's bad in production, or that was the faulty vendor, or that's, whatever.
Okay.
We'll discount that one because we have to show that they all pass. So get another unit. I actually ran into that once in a lab, and it was like in the factory I was working in.
Yeah.
I said, "What are you doing?" He says, "Well, we have to keep testing it until it passes." I said, how many times do you test it? Well, until it passes.
I know.
Sometimes it takes a couple of days.
No, and that's it. When you tell them it's a test, they look at it as a pass, as opposed to a discovery process, which is what a HALT is. And then HAS is a test.
Yeah.
HAS is a test.
It's a screen. It's a better name for
screen.
it. Yeah.
Okay, screen. Something that if
it's going to filter out the good from the bad. I like the term screen. Whereas test, and I had that discussion with Gregg way back when. It's like, why do you call it a test? Because people immediately think they can pass it. And
right.
He goes, they don't understand. And I says, well, change the name. Oh, I wrote the book.
I know. Gregg was very hard to, and I think people that are really inventive and have a lot of ideas and get success with certain ideas believe they really are invincible. And Gregg, I had many, many conversations where I said, no, don't say that anymore, Gregg. That's not really the case, and he would still use it. But he didn't come up with any ideas about how I believe one of the strong things, especially with so many systems really being digital now, is the thermal interaction and timing and voltage, and using that in the HALT methodology approach in step stress and boundary comparisons, what I call boundary limit comparison,
Mm-hmm, mm-hmm.
and using that to understand the variation in the product, or how you can more finely tune a screen to filter out or to screen out those systems that are, first of all, HALT is to build a more robust system.
Yeah.
Once you've done that, then you apply as many unique stresses combined to make a short as possible screen that discriminates with.
Well, and it's aimed at helping you get the production line and supply chain up and running.
Right, and you hope you don't do it very long. You
That's
don't
right.
want to
Yeah,
run
it's not something permanent. But
no,
one of the things,
expensive.
but in this question that you got, she was talking about, trying to set this stuff up. And so one of the barriers was the working with a remote team that just doesn't want to recognize or is blind to this is a useful bit of information as opposed to passing the test. And I've seen that all over the place. That's just one of the biggest hurdles to getting people to understand this concept.
And a little bit is cultural, I believe. And the fact,
seen it all over the place.
You've seen it all over the place. Maybe, yes. You said you're in European countries, they know everything, and they, and that's true. In fact, everybody knows everything. That's why, the advanced engineering department at Storage Tech called it SMART testing, stress margin and robustness testing. Okay, this is another
name.
We only do SMART testing.
Well, HP, we did strife. We called it something completely different.
Life, stress is life, or whatever.
Yeah. No, it was, so there's lots of ways to do it. So she had another question, didn't she?
How do you test for a photodiode, potentially a photodiode failure or a photodiode?
Well, the only answer when I read that question was, how do you test this photodiode for avalanche photodiode for failure? And they're like, well, how does it fail? What's the failure mechanism?
Are you talking as a catastrophic failure? Then you can do a neat failure analysis on the device itself, Yeah.
Or is it
part of the
victim
system
of something else? Did the power supply surge it and it got overstressed and it failed? Or did it manufacture it incorrectly?
Or did you design it too tightly for the variation in the photodiode's parametrics? Is there's too much variation in the manufacturing?
Are you spray painting the surfaces so that it can't see anything? What's the failure? I mean, how do you test anything? One was, well, what's the point?
Right.
What are you trying to learn? Right.
And if you don't know why it's failing, that's what you're focused on. Is you got to reproduce it. If it's intermittent, that's a real challenge.
It is a real
But
challenge.
I guarantee that there is some stress out there that will induce that intermittent to be more frequent, be very frequent.
Yeah.
Or in fact, you can do it every single time you put that stress in.
Well, you got to understand. I think that's the first part before you run a test. I'm a big advocate of the testing is your last resort because it's expensive and it's a crapshoot whether you get good information because we never get enough samples, kind of thing.
Well, testing is the last resort.
But you need to do the due diligence to go. You can't just say, all right, we're going to throw it in some chambers. And you've heard that before. We've got a new product. Let's throw it in some chambers and see what happens. And
no, you need to do a better analysis, a failure analysis. You need to do an understanding, either from your past products or whatever.
Literature search or talk to the vendors if they're going to, talk to you about it. Or
unless you're just out of college, you've been in a company that's had failures. If you worked, more than 5 years in any electronic manufacturing company or assembly, you know of many failures, probably.
Also takes us a week. What are you talking about?
Depending on how bad they are, but yeah. So,
well, I think that's not the right phrase there, Kirk. Is how bad they are. It's how good are they? Are they recognizing failures and doing something?
Exactly.
So if the charter is, well, we got to test this so that we don't have these problems. Is that a screen, right? Or are you evaluating different vendors' options? Which ones meet your requirement?
Exactly.
What is it you're trying to accomplish?
Vendor? Yeah. Exactly.
What is it you're trying to accomplish? What is the test supposed to reveal or provide
Right.
information on.
Right.
It's not just, oh, how do I test these things? I'm thinking
No,
of
what's the
electrolytic,
failure? Right.
like capacitors.
Yeah.
There's somebody asked me a couple weeks ago, and I mentioned it to a couple other hosts, is there a listing of all the failure mechanisms, from material science point of view? I'm like, no. there's books and books and books just on polypropylene, right? Of all the ways that it can be shaped and formed and processed and everything else, and all the various ways it can fail and where it works and where it doesn't work. That's how material science thinks, is what's its boundaries, or where it's useful and not useful. What are the properties and how do they behave? But it doesn't have an index of all the failure mechanisms.
No,
and
the
that's
permutations.
you can get a PhD just on polypropylene, and it's
Right,
just a
and-
raw material. And then you can have a PhD just on one alloy of steel. And
It's like also saying how many ways can this process go wrong?
it's only got one step, Kirk. It's only got one step. How many ways can it run? Oh, about 50.
Yeah, about
Easy.
50. Look at
that
it.
we can think of.
Yeah, you've got, somebody supplying the chemicals, somebody supplying, and each one of them has a long supply chain, like
Oh, geez. Yeah,
just an IC, for instance. You've got epoxies, you've got lead frames, you got wire bonds. I mean, that's just one tiny little device.
Well, just use the epoxy, the overcoat, the little black
Right.
overcoat, right? It's
Right.
black because there's carbon black in it, and then there's also flame retardant in it. And one of the biggest failures we ever had, I ran across, it was just class across all kinds of components, was the epoxy. See, the IC vendor would buy the epoxy to apply.
Right.
Once they put the chip down, they goop this stuff on it and cure it. But they would buy the epoxy, and the epoxy people would blend it with this flame retardant, which they bought from somebody else. And the flame retardant people, for whatever reason, changed the mesh size so that they had different particle sizes. So this is 4 steps up from where we're trying to assemble these things. Right. And there's no way we were going to go investigate the vendor's vendor, to
Exactly.
sort out their processes.
Exactly.
And it was just ridiculous how far back it went through. But
Right.
it was amazing that, everybody in the chain cooperated and did due diligence, and
Right.
we actually were able to sort it out. But it was absolutely phenomenal. You're exactly right. Just the simple thing, like just the overcoating, the
Right.
encapsulant for
Right.
thing is amazingly complex in and of itself.
Right.
And that's not even talking about the IC and all the ways it can fail.
And as mismatches of TCEs, that those epoxies are very proprietary as far as making sure the expansion is correlates with the chip, so that there's not a differential in expansion.
Yep.
But it's as that now the flip chip makes it a little different. I don't know the mechanisms there, but if you just you're talking about now mounting the chip right onto the board.
Yep. Skip all that packaging.
Yeah, exactly. And then of course that makes it more reliable in general. And that
we've seen those in calculators for years. They would do a bare chip on the board.
Yeah.
And just put a dab of epoxy over the top of the whole thing.
Right.
And that's been around for decades and decades.
I know, and conformal coatings, things like that. So anyway.
But she's trying to set up a test for some diode, and it's there. In my mind, the standards bodies saying, oh, well, like in our last episode, I talked about the guy that said for capacitor, for crystals, to make sure they're robust, we're going to drop it 10 times on the carpet. And if it's still good, it's still good. And I'm like, okay. And it's probably a standard someplace, but the standard might give you the process or procedure to apply stresses to something, but I think it's the engineer's responsibility to figure out, well, what stresses are we applying? Will this excite the failure mechanisms that we're interested in learning about, like doing a HALT, or will it excite failure mechanisms that we know exist, like in a screen or a comparison? And so to answer a question is, how do I test these things? Well, start with what you're trying to accomplish, and then back
Yeah.
up for how do you create an experiment, not a test, an experiment that would create the results that you're expecting to see. And if you don't see those, well, maybe that condition doesn't exist, or you have a good part or a bad part that doesn't have that feature or whatever. But you have to design your test like an experiment, with
Right.
starting with your hypothesis right up front. And
Right.
so many people, we all learned that in school, but did we all sleepwalk through it? Come on, it still applies.
Well, right. And it's very important that right, what it is that you're trying, the underlying physics of the failure or whatever it is. You may be blaming it on a diode when it's actually the power supply or something that it's attached to. So it's just, and I didn't get the feeling that this was understood as a hard failure,
Mm-hmm.
or an intermittent failure, operational limit only, or limit
is
failure.
This part of failure
Resettable?
analysis, or is this part of process, control thing, or what are you
How
trying
is
to
it
do?
right? How is it determined that this might be the component that's a problem?
Yep.
And there's just so many questions you start asking, and it's almost impossible to do it on an email type exchange or even a discussion. You really have to have your hands on it. You have to look at the device. You have to open it up. You have to see what it's attached to, what the circuit is.
I'm getting older. I don't know if I'm getting older, Kirk, because I can't see as well as these components, or the components are getting smaller. I suspect it's a little bit of both.
Right. Components have gotten so incredibly small that, without a microscope, you're lost.
Yeah.
Like an 0402 component, tinier than a grain of sand.
Well, you got stuff that's half that size. It's 02 something, They changed the scale on the second two numbers.
Yeah, it's something that a human couldn't put together. It's now the pick and place and all that you couldn't even see it. And so it's amazing. But I just say that you first have to understand what you're trying to, what the mechanism is, what's causing the failure. Then you're trying to determine the best way to stimulate that failure, and then compare that with with past product, or if this diode was used in another product and wasn't a problem, then go to some of those old diodes or something and see if it's a manufacturing variation that's just
or is it a design issue? It opens up so many.
Right. And it takes a lot, and especially if you're trying to do this to a remote lab halfway across the world, you're not. I think it just attenuates everything by about 80% in trying to get an efficient test developed. They can do it. I've known certain groups over there that are really motivated by this.
Well, you have to find one or two champions that's kind of in sync. Especially if you're trying to do a HALT remotely, is you got to have somebody on site that says, we really want to find failures.
Right, exactly.
And we want to do the failure analysis. You
have to have a champion on site to lead the team, to look at it from the frame of reference of discovery, not to pass the test or, it's a whole different cultural orientation.
And it's not just HALT that I've run into that problem. It's sending products back to a vendor, in that's universal.
Right.
It's not our fault.
Right.
You did something wrong. And you get one of the 5 standard answers. And the issue is that, well, this is too much work, I'm not going to bother with it. Or they don't have the resources to do it because we've stripped them all profit, basically, so they can't hire an engineer to do it. But anyway, I digress. So hopefully you got an answer back to her questions, and some of what we talked about made sense.
There were more questions to her. It's like 2,500 more questions I'd have to ask, but It reminds me just quickly that, one of the vendors, when they sent back power supplies, one of the big companies' vendors, when they sent back power supplies, if they found a customer-induced failure, CIF, they would, not credit the company. They would not refund money to and one of them, they would even do it if they saw a pencil mark or pencil writing on the power outside of the power supply.
Oh, really? That lead would be custom
Yeah,
CIF,
that would be
no warranty
anything
expense.
that could identify, a cosmetic flaw on the outside of they
Ding
put
you
it
for
into the
that.
plastic. Yeah, well, of course they would. So, looking into the power supply and investigating any further was probably not something they did very often. Not that I saw.
That's amazing. Yeah, no, that's probably a whole nother episode.
Yeah, okay.
Working with vendors' failure analysis. Some are better than others, but we'll leave it at that. So anyway, got a couple of good questions there. If you've got questions, usually Kirk and I end up with way more questions on, especially how do I test something, and something like that just kind of blows up. But if you've got questions, let us know. Head over to accendoreliability.com/go/SOR, and you can leave us a message there, or you can get a hold of Kirk or I or the other hosts of the show through LinkedIn or through our About pages. So plenty of ways for you to get in touch. One of the things we really do enjoy is fielding questions from people in the works, doing day-to-day stuff and
That's right.
and making progress. And so we learn a little bit about what's going on and what the challenges are that we're facing. And you get some another perspective, not always a straight answer, but usually a way to look at a problem, if not good resources or references to pull from. So part of our charter with this podcast is to talk about reliability, talk shop, and help each other learn as we go. So we'd like to invite you to join the conversation. So with that, Kirk, I think we'll head off for the rest of our day and see what happens.
Okay, Fred, you have a good one, and we look forward to hearing from our listeners for more questions.
Yep, definitely. Thanks, Kirk.
Okay, thanks, Fred. Bye.
Thanks for listening to Speaking of Reliability. We invite you to join the conversation. If you have a question or a topic that you think we should discuss in a future show, please let us know. You can find a comment box below the episode show notes, or just leave a note as part of a review on iTunes.